Welcome to the second lecture of ECE 141. In this lecture, we'll be talking about waveform coding techniques. Basically, we're just expanding our knowledge on PCM and actually on how do we represent PCM on a baseband case. What is the baseband? Recall that the baseband includes the zero frequency, basically the low frequencies. Right? More on that later on a later lecture. For now, let's focus on expanding what we know with pulse code modulation. Recall first the building blocks of our source coding. Basically, how do we represent our analog waveform into digital? Is through a three-step process, through sampling, quantizing, and encoding. The sampler discretizes your analog waveform in time by sampling the analog waveform at a fixed interval called the sampling period. And the next step after that is assigning a value on the sampled assigning a value on the sampled signal depending on how close it is to an amplitude level of the quantizer. So basically, the sampler discretizes with time. The quantizer discretizes with the signal level, let's call it big A. Once we have the level from the quantizer, we encode it or we represent it as bits or a series of bits. And that's your pulse code modulation. Okay? So the pulse code modulation basically maps your discrete set of values into bits. Now, depending on the number of levels, you need to assign an appropriate number of bits. If you want to represent the signal more accurately, you need to have more levels. But to have more levels, you need to have more bits. And to completely represent the number of levels that you're using, you need to, your number of bits rather, should be greater than or equal to the logarithm of the number of levels base 2. Okay? Right. So this example shows what we call a natural binary mapping. What does that mean? It means the 0 level is equal to 0, 0, 0, and level 7 is equal to 1, 1, 1. Basically, you just convert these decimal values into binary, and that's how we map them or represent them. Actually, not that efficient, but it's what some encoders use. I prefer not to use it when you're going to use communication systems, and you'll see why. Right. So the problem with PCM actually is that it imposes an increase in bandwidth due to the short duration of pulses. So because of this, we have an increased system complexity due to additional quantizers, encoders. If you want to represent the signal more accurately, you need more bits. More bits means more expense. More bits means more system complexity, etc., etc. Basically, it's a slippery slope. Solution, there are actually two solutions. Basically, it depends on what you choose. If you want to increase the system, if you want to increase the spectral efficiency, you have to increase your system complexity. The more complex the system, the greater the spectral efficiency. This is your differential PCM. For our, when you want a simpler system, you need to trade off bandwidth there. That means you increase the bandwidth, which is bad, but you have overall a simpler system. Right? So differential pulse code modulation It's actually from the preliminary idea that our analog signals can be guessed. All right? It can be guessed depending on the current and past values of the signal. All right? If we have knowledge of the past values, we can actually make a good guess about our analog signal. So basically, it stems from inference. So instead of just transmitting signal, let's just transmit the difference between two samples. Right? And if you're transmitting between the difference of two, all right, difference of two or more samples, if basically your current sample, m of k, let's say, is actually a function of your previous sample, and the previous sample, there you go, and so on and so forth. Okay? This actually is a form of low-pass filtering. So this is a form of low-pass filtering in the digital domain. And because of low-pass filtering, your high-frequency components are reduced. However, the price of doing this is its increased complexity. We don't know the actual value of the signal. We need to infer it. Okay? We need to infer the current value of the signal depending on the past inputs. So how do we estimate the current value based on the previous values? Right? So you need to increase your system complexity here. So how do we do that? So given a slowly varying analog signal, which is always the case when you have a sampling frequency, so sampling frequency much greater than the bandwidth of the signal. So for the sampling frequency, your analog signal is slowly varying. If this is not the case, rather, then your analog signal is not slowly varying. We can't use this approximation. So recall the Taylor series approximation. When we perturb in time by a small amount, delta t, which is directly related to your sampling frequency, right? We get this equation according to Taylor series. And since delta t is very small, then this just approaches 0. Also this one. And we have an approximate value of the signal based on the current signal and the change in the signal. Right? And if we discretize this, your m of t plus delta t becomes m of k plus 1. This is the value at the next sample. It's approximately equal to the value at the current sample, and depending on the change right here. Okay? So the change in your signal is equal to the current value minus the past value all over your time difference, which is actually the sampling frequency. Sorry, the sampling period. So this will cancel each other out, and you'll be left with this equation right here. So an estimate of the signal, okay, an estimate of the signal can be taken from the current and the past value. Okay? And this is just your first order approximation. If we increase the number of terms, if we include this right here and this right here, instead of assuming that they are 0, then we can have a more accurate approximation of our signal. Right? And this is how you implement that. So we call this the linear predictor, which is basically just a low-pass filter. So this is a low-pass filter in the digital domain. Okay? So a linear predictor is used to estimate the next value. Okay? And we actually use the predictor also to transmit the difference in values. Okay? So that's how we transmit our DPCM. Okay. For delta modulation, so DPCM implementation is very complex. What if we don't want a complex system? We can use delta modulation for that. So a delta modulation always uses a 1-bit quantizer. Right? It only uses a 1-bit quantizer. It's either 1 or 0. Does it increase or does it decrease? Right? So what happens if we implement this? This is what happens. If this is your signal, the black line, your output signal from your delta modulation would look like this. If the signal is greater than the current value at the output, your delta modulation would increase by 1 step. Okay? Once your delta modulation exceeds the current value, it will decrease by 1 step. Right? But the problem with delta modulation is the presence of this. If we have a slowly varying signal, then your delta modulation will just cycle between 2 states on and on. Okay? So we call this the granular noise. If your delta modulation is very slow and your signal is too fast, you can see a large gap between these two signals right here. And this is now your slope overload distortion. Okay? Basically, your delta modulator couldn't keep up with the fast fluctuation of the signal. Okay? To summarize all that, well, basically, there's a trade-off between system complexity and transmission bandwidth. Okay? So if you want decreased transmission bandwidth, you need to increase your complexity. And these are the improvements of your pulse code modulation. Alright. Now, how do we represent our bits as a physical signal? We can represent them as voltages. Maybe we let the bit 1 be on and the bit 0 be off. Okay? So we can represent our bits as voltages depending on the voltage level. If it's on, then it's 1. If it's off, then it's 0. It's actually kind of intuitive. Okay? So this process of representing our binary digits as a physical signal over a line or a wire or radio frequency or fiber. Okay? Basically a mapping of your bits to your electrical signals. This is a process called line coding. Okay? So the transmission requirements for that is that we need a small transmission bandwidth, easy clock recovery. What does this mean? It means that we can easily synchronize. And a close to 0 DC value. So we don't want any DC on our lines. And capable of detecting bit errors. Right. So some coding classification. Our unipolar signaling is, or what we call the on-off keying. Basically, we represent 1 as positive A, 0 as 0. So this is unipolar signaling. So it's simple implementation because you only need one voltage supply, However, the DC value of this signal is certainly not 0. Okay? Polar signaling, basically your 1 is still positive, but your 0 is negative. And as you can see, the DC bias of this signal is 0. Okay? So that's the difference between your unipolar and polar signaling. Okay? Another type of line encoding is the bipolar signaling or alternate mark version. So it depends on the previous state. Basically, the ones trigger either a positive or a negative, but the 0 will always be 0. Okay? So if it became positive A at this one, the next one would have a value of negative A. And this actually eliminates DC buildup on the cable because we don't want that. And this is regardless of the probability of occurrence of ones and zeros. Okay? Also has a smaller transmission bandwidth compared to your unipolar and polar. Okay? So if you compare them, your unipolar would just switch when there is 1 between 1 and 0. If we have an alternating 1 0 1 0, then we have a square wave. Same with polar signaling. But for this, well, the alternating pattern would have the same bandwidth as your alternating pattern here. But what if we have some pattern like this 1 0 0 1 0 0 and on? As you can see, the pulse here has the pulse period here is less compared to this value right here, or the pulse value right there, or the distance between pulses right there. Okay, so that's how this bipolar signaling alternate mark basically has a smaller transmission bandwidth. And one more thing that is good about this type of line coding is that it provides error detection. So every bit errors in bipolar variation can be detected, right? So if we have 2 consecutive positive A's, then there's something wrong. All right. It also guarantees timing recovery. So if there is a long run of ones, let's say just 1 1 1 1, that means the signal becomes kind of like a clock. Okay? So it alternates between 2 states always if you have a string of ones. Right. So the next two would be what we call the next two would basically define how the pulse behaves. Alright? So a non-return-to-zero pulse, basically, you have a constant voltage level within 1 bit duration. So it has a wider pulse width, which means it has a smaller bandwidth. So you see here. So basically, your signal does not return to 0 over the duration of your bit period. As compared to return to 0, the voltage level, quote unquote, returns to 0 at exactly half the bit period. So the bit period right here, as you can see, for 1 it's positive A, and it will return to 0 when it approaches half the bit period. So the problem here is that the pulse width is smaller, which makes the transmission bandwidth larger. However, the timing information for the return to 0 case is actually easily extracted. Right. So another example is your split phase or Manchester signaling. Okay. So the Manchester signaling right here, as you can see from, as you can see from this image. So the 0 and 1 pulses are always in transition at the middle of a bit interval. Okay? So what does that mean? So as you can see from the signal here, if it's a 1, then it will always start from positive A to negative A. So from here to here, your 1 always starts from positive A to negative A. Your 0 starts from negative A to positive A. Okay? So the 0 and 1 always defines the transition at the middle of a bit interval. Okay? Instead of defining 1 and 0 as the levels, so as you can see here, right here, instead of defining 1 and 0 as signal levels, we define 1 and 0 as a transition. Okay? So at the middle of the bit levels, you will identify a transition, and depending on the previous and the current value, okay, you determine the value of the bit. Okay? And this is actually a good way to extract the timing. So instead of encoding the signal here at the value of the level, you're encoding the signal here at the transition. And every transition creates a timing opportunity. And of course, if you can see this signal right here, assuming equiprobable 1 and 0, the signal actually has 0 DC component. And this is what we commonly use in our wired Ethernet and some near-field RF applications. Right. So you want to know their frequency domain. So you can simplify actually the analysis of PSD by representing them as values A sub k as an impulse train. Okay? So this is your impulse train. It's 1 if it's standing at the positive side. It's 0 if it's standing at the negative side. And you plug them in a pulse P of t, which results into the line code of what you want. Right? In this case, it's just your bipolar signaling. Right? With this, we can actually represent the PSD of your output. Okay? So the PSD is equal to the absolute value of the frequency spectrum of your pulse squared times the spectral density of your x of t. Okay? So why are we considering spectral density? It's because the output bits are random. Since it's a random process, okay, then it doesn't have a defined frequency spectrum. But we can actually know the power spectrum or power spectral density. So with that, we know how much power it has on a certain frequency. That's what we are certain about. We're not certain of the current output of your random process, but we are certain of how much power it has at a certain frequency. That's your power spectral density. Right? So for P of t, for your on-off keying or your bipolar signaling, it's actually just a rectangular pulse. And we already know that the rectangular pulse has a sync-shaped spectrum. So now, how does our impulse train affect the power spectral density right here? So recall first using Wiener-Khinchin theorem. Our power spectral density is just a Fourier transform of the autocorrelation function. For the impulse train, it's equal to this. Okay? And R sub n here represents the sum of your values on your impulse train. Okay? Depending on the delay, which is defined by n right here. Okay? So the delay is defined by n. So at n is equal to 0, then we have basically n equals to 0 means there's no delay. Then we're just overlapping the signal with itself. Okay? So I'll leave it to you as an exercise on how to prove this. Okay? So the general form of the PSD can be represented as, so we have your pulse spectrum, and this is your spectral density of your impulse train. Okay? So generally, if we compare a return to zero and a non-return to zero signaling, it means when you look at this comparison, we know that the return to zero signaling has a smaller pulse compared to your non-return to zero. So that means the spectrum of your NRZ has a smaller bandwidth as compared to the spectrum of your return to zero. Okay, so just some notes, some FYI. Now let's proceed to the solution. So for uncorrelated messages, this should be E. Okay, so this is E. For uncorrelated messages, what does that mean? It means that if you have a time shift that is non-zero, your autocorrelation will just be noise. Okay? At time n is equal to 0, your autocorrelation is equal to some what do you call this? Variance. Okay? This variance is the variance of your outputs right here, the output train. Okay? It's the variance of that. Plus some noise M sub A. Okay? So the frequency domain of the autocorrelation function can now be rewritten as this one. Okay? And using the Poisson sum formula, your frequency domain equivalent becomes this value right here. Thus, our Sy of f becomes this expression right here. For polar signaling, since A sub k is either +1 or -1 and are equally likely, then if a delay of 0, so if we have a delay of 0, okay, if we have a delay of 0, then we're just getting the average of your A sub k squared, which is either +1 or -1. If you take the square of that, it's just 1. Okay, and then we get a value of R sub 0 equals 1. If A sub k is, if we're gonna get the autocorrelation at some delay that is not 0, then since your +1 and -1 are independent and equally likely to occur, then this sum would be 0. So this is actually, this is not noise, I forgot. It's actually a DC component, this MA squared right here. Okay? And finally, the polar signals will have this power spectral density function right here. So if you look at that, then we have this sync function that represents the power spectral density of a polar signal. For on-off keying, so it's either +1 or 0 and are equally likely, then the DC level is equal to 1/2. When there's a delay, then that 1/2 becomes 1/4. Right? So the PSD of your on-off keying becomes this expression right here. So you can try to prove it yourself. If you compare it from here to here, it has some sort of sum of delta functions, the graph of which looks like this. So we have this impulse train within the sync pulse, and it doesn't provide us any information. So it's just basically a waste of power. Okay? Basically a waste of power. So that's the difference between your polar and unipolar and bipolar signaling. Alright? Right, so from here you have your polar, from here you have your unipolar. Right, so now let's move on to discussing the self-synchronization of your line codes. So your NRZ codes can be more problematic when you want to synchronize them. If you have a long string of 0, since there are no transitions, again note that transitions create synchronization. If you have a long string of zeros or a long string of ones, okay, we can lose our synchronization since we cannot detect any transition in the signal. The upside to that is it has less bandwidth. Okay? So what we do to synchronize the signals properly is that we limit the long consecutive runs of 1 and 0 by forcing bit changes after a given number of bits. We call that bit stuffing. However, since it's just a stuffed bit, it doesn't provide us with any information, and you actually kind of lose some data right there. So it's kind of a reduction in throughput, or reduction in bits per second. Okay? For a return to zero signaling, well, if you just take the absolute value of a return to zero signaling, you get some form of clock right here, a signal that always transitions at the bit changes. And again, any transition would provide us with timing information. So this is an advantage of your polar return to zero signaling. Okay? So basically, we have a better timing information in exchange for bandwidth. Right? So that's the end of this lecture. If you have any questions or clarifications, don't hesitate to post in the comment section below. So I'll answer it as soon as possible again. Thank you for listening. See you in the next lecture.